Let's talk about the entropy and Gibbs free energy of mixing. We saw for ideal gases that the delta S of mixing was equal to negative NR XA log XA plus XB log XB. And this was just for a binary mixture of ideal gases. If you had more gases, then you just add them on, add all the terms up, on and on and on and on. Conveniently, it's the same for mixtures of liquids. So that's really nice. What about the Gibbs free energy? Delta G of mixing is going to equal delta H of mixing minus T delta S of mixing. And T delta S just goes right in there. So then what about the enthalpy of mixing? Well, for ideal solutions, we saw on a previous slide that for ideal solutions, the delta H of mixing is just 0. So that's real convenient for our Gibbs free energy of mixing. Then it just equals negative T delta S. So that's just nRT, and then the sum over all the components I, mole fraction of I, log mole fraction of I. Exactly the same as it was for ideal gases. One final quick note, I want to remind you why for an ideal solution the enthalpy of mixing is 0. Remember, that's because the interactions between A and B are no stronger or weaker than A was to A or B was to B. So that means there's no change in potential energy to mix those two solutions together. So therefore, there's no enthalpy change. Okay, let's talk about this clicker quiz question. If you haven't done this one on Canvas, go online and do it now. So here's the question. Which observation would lead to the conclusion that a mixture of liquid A and liquid B created a non-ideal solution? Okay. Upon mixing, here's the first possibility. Upon mixing, there is no change in mass of the system. Well, according to the law of conservation of mass, no matter what we do in chemistry, we're not going to be changing the mass of the system. So that would actually be true for ideal or non-ideal solutions. So that's not helpful. That's not the right answer. Number 2, upon mixing, the temperature remains constant. Well, if the temperature remains constant, that would imply that delta H was equal to 0, possibly. But this would actually indicate an ideal solution, so that's not the right answer. We're looking for an indication for a non-ideal solution. Number 3, the volume of the final solution was greater than the sum of the volumes of the two pure liquids. So what does volume have to do with non-ideal solutions? Well, it turns out that these intermolecular forces, if they change, then they're going to push or pull the molecules together or push them further apart. So that would actually be an indication that there is a change in the interaction forces. So this is the correct answer. Number 4, the entropy of the final solution was greater than the sum of the entropies of the two pure liquids. As we saw in the last slide, the entropy of mixing will increase even for an ideal solution. So that's not correct. Okay, last slide for the day. Let's talk about binary mixtures. I want to draw your attention to a number of important variables. We've seen X refer to mole fractions. So for the rest of this chapter, we're going to be using the symbol X to represent the liquid mole fractions. we're going to be using Y to represent the vapor mole fraction. So this is a bit of a tricky switch here. And then Z is going to be the total mole fractions in both the liquid and the vapor phase. This is going to be a little bit complicated because if there is a small amount of vapor, then Z is going to be very similar to X. And if there's a relatively small amount of liquid, then Z is going to be very similar to Y. So just keep that in mind as we move forward here. The book has a fairly complicated and fairly complete description of how to relate a number of these variables to each other. And I'm just going to give you the punchlines here. You can read the chapter to get a better idea of where all of these equations come from. But remember, what we're considering here is a mixture, binary mixture of liquids A and B. And above it, of course, there is a vapor phase of A and B as well. Now, in general, even for ideal solutions, the proportions are not going to be equal. So that means the mole fraction in the liquid phase is not going to equal the mole fraction in the vapor phase for both components. So a number of different equations tell us what those are going to be, and I'm going to write down each of these important equations here. Again, look in the book chapter to get where these come from. The total pressure is going to be equal to the mole fraction of A times the vapor pressure of pure A minus the vapor pressure of pure B plus the vapor pressure of pure B. So that's the first key equation. The next one, what does the mole fraction of A equal? It's going to equal that total pressure minus the vapor pressure of pure B divided by vapor pressure of pure A minus vapor pressure of pure B. What about Y? This is the mole fraction in the vapor phase, remember. This is going to equal the vapor pressure of pure A, total pressure, minus vapor pressure of pure B, divided by total pressure, pure A minus pure B. Now the last equation is relating the total pressure to the mole fraction of Y, because up here we are relating the total pressure to the mole fraction X, which is the liquid state. But what about the vapor state? It's going to be pure A, pure B, partial pressures, vapor pressures, pure A, vapor pressure, pure B vapor pressure minus pure A vapor pressure times that mole fraction in the vapor state. Okay. Let's take a look at what each of these represent. I'm going to recreate these plots up here because I want to talk about them. Let's say on this axis I have the mole fraction in the liquid state of component A. I can go from 0 to 1. This is pure B, and this right here is pure A. Okay? And then over here on this plot, I'm going to have the total pressure of the vapor above the solution. So if I had pure B, then hopefully you recognize that this is going to equal the vapor pressure of pure B. And then over here, since that is just pure A, that's going to be the vapor pressure of pure A. And this line is going to be linear. Okay? So that's how the liquid mole fraction determines the total pressure of the system. But now, if I want to plot y, and I have the total pressure of the pure system, again, here is pure B, here is pure A. I'm going to have those dots in the same place. This is going to be PB star, this is going to be PA star. However, now I've got a differently shaped curve. It's not a straight line anymore. And that's depicted up here in this plot. So this may be a bit of an unexpected result for you, but this is somewhat similar to the example I gave earlier, where the mole fraction in the liquid state is going to be different from the mole fraction in the vapor state for no other reason than just the two substances are going to have different vapor pressures. This will come into play a lot more when we get to the subjects we'll talk about on Monday.